Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler and today we're going to be doing Unit 8, Lesson number 5, the geometry of the dot product. This is going to be our last lesson in the introductory unit in vectors. And one of the main tools that we saw in the last lesson was the dot product. The dot product is mainly a geometric tool that allows us to understand, especially in three-dimensional vectors, which way vectors are pointing relative to one another. And that's what we're going to be working on today. So let's get right into it. Exercise number 1 is actually a review problem from our last lesson. We've got two vectors in 3 space, and the question is, what is the angle that's made by connecting the vectors tail to tail? In other words, if I had vector u pointing in 3 space and I had, vector v pointing in 3 space, what would be the angle in between them, right? So I'd like you to pause the video right now and work through this. Make sure that you express your angle in degrees and express it to 3 decimal place accuracy. Pause the video now. All right, let's go through this review problem. This is a very, very standard problem. Remember, what we know is that the dot product of two vectors, by definition, is the magnitude of the two vectors multiplied together times the cosine of the angle in between them, right? And that's what we're looking for here. Now the key is that we can figure out u dot v by doing this shortcut method, i.e. we take the x component of u, multiply it by the x component of v, the y component of u multiplied by the y component of v, and the z component of u times the z component, which I can't see very well, sorry about that. And then I just I just rack those all up. And what I found is that the dot product is equal to negative 11. So I have this portion. These two things we can find using that extended Pythagorean theorem, right? So the magnitude of u is the square root of negative 2 squared plus 7 squared plus negative 3 squared. This is going to be a little bit ugly, but we're going to get the square root of 62, right? Then we can find the magnitude of v. Again, extended Pythagorean theorem, square the 6, square 1, square 2. We get root 41. And now we have a very nice equation, right? We can say, negative 11 is equal to the square root of 62 times the square root of 41 times the cosine of theta. So the cosine of theta is negative 11 divided by root 62, root 41. One of the great things about cosine, we talked about this in the last lesson, cosine is unambiguous, meaning that you can simply do the inverse cosine now of this quantity. I'm not going to rewrite it. And that gives you your angle. It's very nice. It's 102.602 degrees. If you wanted to, of course, you could work out this intermediate step in terms of a decimal. If you did that, let me give it to you, negative 0.28. I don't have these things. Whoops, 21817, etc. But there we go, right? So these two vectors are at a slightly obtuse angle with one another. So the picture is actually incorrectly drawn. It's more like this, and just a little bit more than 90, something like that. Okay, this is a very important problem to start off. Really important that you understand why that worked out that way. So pause the video if you need to, because I'm going to scrub out the text. Okay, here we go. All right, so let's take a look at another geometry problem. The dot product is all about alignment, all about alignment of two vectors. So exercise 2 is again a review problem. It says, which of the following vectors is perpendicular to this 2-space vector, and how do you know? Right? How do you know? So think about that for a moment. Remember perpendicular, right? 90-degree angles to one another. All right. Well, in 2 dimensions, it's not too difficult, right? The key is, as always, that u dot v, the dot product, is equal to the magnitude of u times the magnitude of v times the cosine of theta. If it's perpendicular, right, if theta is 90 degrees, well, then cosine theta will be 0. And that means the dot product will be 0. we can reverse that logic and say that if the dot product is 0, then the cosine is 0, and if the cosine is 0, then the angle is 90. So what we're looking for is which one of these 5 vectors, when dotted into 6i minus 9j, would give us a dot product of 0. Just take a look. Well, actually, I'll leave that. Just take a look at letter A, right? If we did u dot v here, right, what we would get is negative 36 and then negative 27. So that obviously would not combine to be 0. In fact, if you work on it for a while, what you find is you find it's choice D, right? If I do u dot v here, I'll find that I get 6 times 6, which is 36, and 4 times negative 9 is negative 36, and I'll get 0, right? So, simple enough. Simple enough. You could use information about things like negative reciprocal slopes from geometry to be able to solve exercise 2. But that would be much, much harder if you were in the 3-space situation, so vectors with 3 components to them. Then the dot product is definitely the way to go. But very, very important. If a dot product is 0, then the 2 vectors are perpendicular to each other, assuming that neither one of them is the 0 vector. Now, exercise 3 says, based on the dot product alone, would the following 3-space vectors be somewhat aligned or somewhat opposite? Explain. So, well, what I'd like you to do is find the dot product using the shortcut. And then think about these terms, somewhat aligned or somewhat opposite. Then we'll talk about them. But find the dot product first. All right, well, let's do it real quick. U dot v, right? We'll have 4 times negative 5 plus negative 2 times negative 8 plus positive 6 times positive 3. Work that all out and we get 14. Now, the actual number 14 doesn't tell you that much, but what it does tell you, again, let me write down the definition, right? What it does tell you is that the cosine of the angle must be positive. Now remember why that is, right? So this implies this. This is definitely a positive number. This is definitely a positive number. The only thing that could possibly be negative is cosine. So if the dot product is positive, well then cosine must be positive. And if the dot product is negative, cosine must be negative. Now if cosine is greater than 0, what that means is that theta must be in this range. Okay, watch how careful I'm being. It's greater than or equal to 0, but less than 90. Right, if it were equal to 90, the cosine would be 0. So we would say that these vectors are somewhat aligned. Somewhat aligned, meaning that they look kind of like this, right? U and V. What they don't look like is this, right? This would be somewhat opposite, right? So they don't look like this. Now you might ask, well, why aren't they totally aligned? Well, that I can tell for certain, right? 2 vectors will be totally aligned if one of them is a scalar multiple of another. So, like for instance, you got your u here, which is 4 comma negative 2 comma 6. If I came along and I multiplied, let's say, everything by 3, so I got 12 comma negative 6 comma 18. These 2 vectors would be totally aligned. They point in exactly the same direction because all that second vector is sort of the first vector stretched out by a length of 3 or stretched out by a factor of 3. All right, that's clearly not the case here. Right? Clearly not the case. So I'm going to clear all this text out. Make sure to really think about this and write it down. Okay. All right, let's get rid of it. So the alignment of 2 vectors. The alignment of 2 vectors is all about the dot product. If a dot product is equal to 0, then the 2 vectors are perpendicular. Very, very important. If the dot product is greater than 0, then the angle must be between 0 and 90, and the vectors are either fully aligned, they're parallel to each other, or they're somewhat aligned. And again, the fully aligned is simple. If one of them is simply a positive multiple of the other, they're fully aligned. On the other hand, if the dot product is negative, then there must be an obtuse angle between the two vectors, and they're either fully opposite, anti-parallel, or somewhat opposite. Now again, fully opposite is very simple, right? It's the same thing as sort of being fully aligned, except you've multiplied the vector by some negative constant to sort of, if you will, flip it, right? So I mean, if I have a vector like this, and then I multiply it, let's say, by -2, all of a sudden it would suddenly look like that. All right? We explored that geometry last time. I'm going to clear out all of this really quick. All right, so let's go back, and let's take a look at exercise 4. Exercise 4 says classify each pair of vectors as either no alignment, somewhat aligned, or somewhat opposite. All right, so see if you can use that test above to evaluate each one of their relationships with one another. All right, let's go through it. So, red. Let's stick with the red. U dot V, what would it be? 7 times 1, -3 times +3, -2. Now, that -2 means that it's either somewhat opposite or fully opposite. I know it's not fully opposite because I can't take U, multiply it by any negative number, and get V. Okay, that's not going to happen. All right, so that means that these are, whoops, let's get rid of that. These are somewhat opposite. Somewhat opposite. All right, that's all I know. Right. Letter B, if I do, let's say, force 1 dotted into force 2, well, I get -4 times 5 is -20. 10 times 2 is +20. That gives me 0. We can either say that there's no alignment, or even better, we can say that they're perpendicular. All right, let's take a look at letter C. Here it appears that we're dotting a velocity into an acceleration. -2 times -3 is +6. -8 times -1 is +8. +14. That means that we're either somewhat aligned or completely parallel. But again, it is not possible to multiply the velocity vector by some scalar constant and get the acceleration vector. So they're not fully aligned, but they are somewhat aligned. All right, and again, it's kind of like think about it this way. If I had like an object, and I was kind of pulling on it in this direction, and I was pulling on it in this direction. Generally speaking, those things are pulling on it, forward, let's say. On the other hand, right, if I had something kind of pulling on it, whoops, and erase part of my object, something pulling on it like that, and something pulling on it like this, right, they're kind of opposing each other. One of those vectors is sort of canceling the other one out a bit. All right? So I'm going to clear out the text. Very simple test, right? It really gets at the dot product. The dot product principally tells us whether vectors are somewhat aligned or somewhat opposite. Again, the complete alignment or the completely opposite alignment, that's all about whether one vector is a scalar multiple of the other. Very simple to tell that. Okay, I'm going to clear out the text. Write down anything you need. Here it goes. All right, there's one last topic we're going to look at with vectors, and this is the most challenging topic of all with dot products, and yet where dot products get used, especially in what would be called typically third semester calculus, is all about vector projections. So let's talk about what a projection is. All right, let's say you had vector v. All right, just vector pointing out here, and let's say you had some other vector u. Typically when we take vectors like vector v, let me go back to blue. Typically when we take a vector like v, we will break it down into its horizontal projection, if you will, v sub x, and its vertical projection. I don't know why I made one of those dashed and one of them not. That's the way that we typically do it. But we could also just ask a very simple question. Well, how... I was trying to erase that. How much of this vector lies in the direction u, right? How much of it lies in the direction u? So let me help you visualize this, right? Or There it is, right? What we're really doing is we're kind of extending u, and we're creating this right triangle, right? And u can be extended forever, but extend it to a point, right, where you can create this right triangle. And then that becomes the projection of v in the direction of u. So in other words, we're not projecting anymore into the x direction and the y direction. We're projecting in the u direction and, I guess, if you will, the perpendicular to u direction. But we're only going to be worried about the projection in the u direction. So we just want to know, how much is this? How big? Can I do that? No, I can't. Oh, well. How big is that red line, right? What is that red line? Okay. Now, in order to do this, and let me clear out that little blue dot. It's a little weird. In order to do this, what we're going to first do is we're going to look at the dot product of vector v with a unit vector. Unit vectors are amazingly important. They're very, very simple, right? A unit vector is simply a vector with a length of 1. All right, so let's take a look. Here's that picture that we had before, but vector v, vector u, and I'm telling you right now, the length of u is 1. All right, so if I looked at vector v and I dotted it into vector u, right, by definition, that'd be the length of v times the length of u times the cosine of the angle. But remember, in this case, what we're doing is we're saying that the length of u is 1, right? So that's just the length of v times cosine theta. Now that should look kind of familiar, right? Right? You should have seen things where you've got like r cosine theta or whatnot, right? Anytime you have a sort of calculation that looks like some kind of constant times the cosine of some angle, then that is literally right triangle trig. And I'm going to rotate this picture a little bit. Right? Let's say this is v, right? And actually, that's not just v. Let's call it the length of v. I'm purposely not extending this far. Let me extend it out in dashed lines. If this is theta, then this is the length of v times cosine theta. And that's exactly what we're looking for. In other words, v dot u gives us the projection of vector v, how much of v lies in the direction of u, but only if u is a unit vector, only if it has a length of 1. But if it has a length of 1, then u dot v, or better yet, v dot u, gives us the projection we're looking for. All right, it's just right triangle trig, because all we get is the length of the hypotenuse, the length of v, times the cosine of the angle, right? V cosine theta. So I mean, take a look. It's very simple. Given that u is a unit vector, find the component of v, where v is equal to 10i plus 35j, in the direction of u. I'll draw this out eventually, but I mean, like, what we just came up with was very simple. I mean, it just is v dot u. That's simple, right? It's going to be 10 times 3/5 plus 35 times negative 4/5. And let's see, what would I get? I'd get 6 minus 28. Is that right? Yeah, that's right. And that's negative 22. So that's it. That's the projection of v in the direction of u. Now you might think, well, God, it's negative. That seems weird. But let me try to show you the way this works. Now, this is a little bit confusing. Okay, think about v. v is 10 to the right, 15 up, right? So it's, I'm sorry, not 10 to the right, 15 up, 10 to the right, 35 up. So much longer here. Let me draw that. All right, so let's say that this is v. Right, u, on the other hand, is 3/5 to the right, so much shorter, and 4/5 down, like this. So this is u. Can't get my tail there. There we go. And the idea of a projection is literally if we extended u backwards, like this, and then we extend this down so it's perpendicular. The question is, how long is that? And that's actually got a length of 22. Okay, the reason that the dot product turns out to be negative, or the projection turns out to be negative, is that we have to go in the opposite direction of u. All right, but literally that gets the job done. Now, a couple things. Okay, thing number one, is the length of u actually 1? Is this actually a unit vector? All right, and it is, right? Think about it. If I took 3/5 and I squared it, and -4/5 and I squared it, I'd get 9/25, 16/25, 25/25. Now, of course, the length is all of this under a square root, but the square root of 1 is 1, so that checks. The other issue is, what happens if u is not a unit vector? Then all this breaks down, it all breaks down, and you're going to address that a little bit in the homework. There's a very easy fix for it. If u is not a unit vector, it's a very easy fix. But if u is a unit vector, all you have to do is dot it into v, and that will tell you how much of vector v lies in the direction of vector u. And I understand that's a little bit complicated, but it's good to have a first exposure at this level so that when you really need to use it and understand it quickly, you've seen it once. All right. I'm going to scrub out the text, so copy down anything you need to. All right, let's get rid of it. Okay, well that was our introductory unit on vectors. We're going to be using vectors now to do all sorts of great things, like looking at parameterization, looking at two-dimensional, maybe even three-dimensional motion in future lessons. Vectors give us a lot of ability now to describe things that have multiple components to them. But we're going to get into that in unit number 9. For now, this has been another Math 4 Honors lesson from Arlington High School. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.